Molecular geometry. In this unit, we're going to talk about an expanded VSEPR theory. We're going to continue the study that we started in the last unit as we're determining geometry of molecules. We'll talk briefly about the role of carbon and the way it's a little different. We'll introduce the concept of valence bond theory with its pi and sigma bonds. And then we will talk about the more complete idea of molecular orbital theory, which looks at the entire molecule. And we will talk about bonding and antibonding. In VSEPR, we're going to review the rules, determine the best shape. Now, that is an interesting process. And talk about the actual geometry of the molecule itself. When we look back over the VSEPR rules, you recall these. Rule number 1, you select the central atom. That's the one you have the least number of. Number 2, you determine the number of electrons about the central atom by counting the valence electrons of the central atom and adding to that 1 for each atom that's attached, except for oxygen and sulfur, which add nothing. Add 1 for each negative charge and deduct 1 for each positive charge. And then rule number 3 is divide the result of step 2 by the value 2. In other words, halve it. And select a geometry from this table. Now watch this table. You're going to notice some changes. Here you see that we have for 2 electron areas, we have a linear geometry. For 3 trigonal planar, 4 tetrahedral, 5 trigonal bipyramidal, 6 is octahedral. And I've given you the bond angles. Now we've added a 4th column here called hybridization. And we will get into that a little bit later, but in this unit. So make sure you keep that new column there. Let's go back and look at some examples. For example, what is the geometry around carbon and carbon dioxide? So you look at the formula and you say, well, carbon has 4. It adds nothing for oxygen, which gives me a total of 4. Divide that by 2, and I get 2. And when you look at the table then, you see that the geometry is linear. So we know the structure is going to be in a straight line. Oxygen to carbon to oxygen. Okay. Now the next one I'm going to review with you is what is the geometry around oxygen and water? Well, we do the same thing. The central atom is oxygen. We have 2 from hydrogen plus the 6 from oxygen, giving us a total of 8. Divide that by 2 and we have 4. So our geometry is tetrahedral. Now, students often ask me, why is carbon dioxide linear and water tetrahedral? Well, here you see it, but let's give you some more information to support that. This is the geometry of water. You have 2 hydrogens at 2 of the 4 points of the tetrahedron and lone pairs at the other 2. Here is a picture of how a model might look. Now I've used kind of an interesting shape there to show you the lone pairs, and you'll understand more about that as we get through some of the other geometries. This angle right here is 109.5 degrees, 109.46 if you really want to be picky. But actually with water it's a little different because you get some repulsion and so forth between the non-bonding electrons, but we'll deal with that later. This angle right here is also, that's what I'm talking about, that approximately 109.5 degrees. When we look at the actual shape of the water molecule, imagine taking away those unshared electron pairs up there. See those 2 unshared electron pairs? Take those away, and when you do, what are you left with? You're left with a bent shape. So the water molecule has an actual bent shape, while the carbon dioxide molecule is actually a straight line, a linear shape. But the geometry of the water molecule is tetrahedral? Let's look at the geometry of ammonia. What is the geometry around nitrogen and ammonia? Now stop and figure. Well, here's the formula, just in case you didn't remember. And what's its geometry now? Well, nitrogen has 5. We pick up 3 from hydrogen, giving us a total of 8. Divide that by 2 and get 4. So our geometry is tetrahedral. What does this look like? It looks like this. We have a tetrahedron. We have hydrogen at 3 of the points of the tetrahedron and a pair of unshared electrons at the 4th point. The bond angles in an ideal world are 109.5 degrees. They're probably a little off of that due to the presence of the unshared pair of electrons, which occupy a larger volume. But we'll get to that later. Here's what it might look like. And imagine, if you will, this lobe up here, this big lobe that I have, is where the unshared pair of electrons reside. Now, the next question is, what is the shape of the molecule? And when we look at the shape of the molecule, we exclude the unshared pair of electrons. So look at it. And how would you describe its shape? Well, here we have this. We take away those electrons, and what do we have? We have a triangular-based pyramid. A triangular-based pyramid. Maybe you can see it better here. A triangular-based pyramid. And those bond angles right there are 109.5 degrees, approximately. You get the idea? Look at phosphorus in PCl5. What's the geometry around the phosphorus? Let's go after this structure. Well, let's see, PCl5. What's central? Yeah, phosphorus. How many does it have? Well, phosphorus has 5, and it picks up 5 from one from each one of the 5 chlorines, giving it a total of 10. Divide that by 2 and get 5. So when you check the table, you'll see the geometry is trigonal bipyramidal. It's like 2 pyramids with their bases touching each other. Their bases plopped together. It's a triangular bipyramidal structure. These bond angles are 90 degrees right here. These bond angles are 120 degrees. And these are 180 degrees. So you have 3 different degrees of angles here. You have 90, 120, and 180 degrees. Let me point out to you 2 different ways we have of looking at bonds. These right here are called equatorial bonds. They go around the equator of the molecule, if you will. So what are those other 2? Well, they are axial bonds. That one and that one. Imagine if you had this molecule and you could spin it, you would spin it on those axial bonds and it would rotate on that axis. Let's look at the geometry of ICl3 now. It's going to give us some interesting things to think about. Let's start first. What is the geometry around the iodine in ICl3? Figure it out. I'll stop for a moment and let you work it through. And did you have 7 plus 3 is 10? Divided by 2 is 5, telling us then that the geometry around the iodine is trigonal bipyramidal. That's where we're going to find electron densities distributed around the iodine. Now here's the structure, the way it looks like. You've got 5 possible spots. Where do the chlorines go? Well, There are three possibilities. We could put the chlorines here. These are all at equatorial positions. That looks good, doesn't it? And what's at the other two spots? Lone pair electrons. So in this one, we have a structure that looks something like this on the model. Okay, got a handle on that? Let's go to another. Here's another one. Now this is also meeting all the requirements. It's trigonobipyramidal. And you've got lone pair electrons in two positions. You see that two of the chlorines are at equatorial positions and one is axial. And the model looks something like this. Yeah. Here is the third one. Now notice we have one chlorine at an equatorial position and two of the chlorines are at axial positions. And lone pair electrons are at the other two spots. And our model looks something like this. Okay. The question is, you know what's at the other locations. Those are all lone pair electrons. But which structure is preferred? Or are they all there? Well, let's look at the one that's preferred first. To select the best structure, we have to distinguish among the possible arrangements, such as in this case in which we have three. And to do this, we're going to use the 90-degree repulsion concept. This is keeping it as simple as possible. We'll compare the repulsions in all the combinations looking at lone pair electrons and bond pair electrons. Now we'll use the expression LP to designate repulsion between two lone pair electrons. And that repulsion is going to be most significant at 90 degrees. That's going to be a really, really strong repulsion at 90 degrees. Now LP-BP will designate a lone pair and a bond pair repelling each other. And yeah, that's going to cause some strain at 90 degrees, but nothing like the lone pair strain is going to be. And the third one is bond pair repulsion. And this is talking about, obviously, repulsion between two bond pairs. This creates very, very little problem, even at 90 degrees. This one is easy for a molecule to tolerate. So lone pair repulsion at 90 degrees is a no-go situation. Well, virtually. Lone pair, bond pair is not good. It's pretty tough. Bond pair repulsions between two bond pairs is fine. That's not a problem. So now let's go back and look at those three. Use this simple rule. When you've got several structures, more than one structure, to be considered, look at it like this. The first thing you do is determine the number and type of those repulsions, just like we've done. But then when you're making a decision about which one of those structures is best, you want to use the fewest number, the structure that has the fewest number of the greatest strain. You want to use 0 lone pair at 90 degrees if at all possible, and as few lone pair bond pair repulsions at 90 degrees as you can get. A good way to put it is like this. Lone pair, more than lone pair, more than bond pair, because this is your greatest strain up in this area up here. Your lone pairs have your greatest strain. Your bond pairs have your lowest strain. So have as many bond pairs as you need at 90 degrees, but not the lone pair. Now granted, we're only working with 90 degrees. Working with repulsions at other conditions is something for a later lecture. Here are our three structures. Let's start right here, if you will, with this structure. Here it is. Now I want you to count the lone pair, 90-degree interactions. Do you see any? Sure. There's one right there. Yeah. Do you see any other lone pair, 90-degree interactions? I don't see any either. Okay, so we've got one. Okay, now count the lone pair, bond pair 90-degree interactions. Do you see any? Sure. There's one there. Here's another one right here. Here's this one right here. You get it? So going back to our comparison of the three, we see that this particular structure has one lone pair interaction and three lone pair bond pair interactions. Okay, let's go look at this one now. And here it is. Now count the lone pair 90-degree interactions. Well, there aren't any. Remember, this is 120 degrees right here. And that's the only place it could possibly occur, and that's 120 degrees, so we don't worry about that one. So there are none in the lone pair 90-degree interactions for this molecule. Well, what about lone pair bond pair 90-degree interactions? Here's one. Did you get that? Yeah. Here's another one right here. Between the bottom one and that, yeah, right there. Here's number 3 right here. And how about it? Do you see another one? Sure, here's number 4 right there. So we have no lone pair 90-degree interactions and 4 lone pair bond pair interactions. So here we've got this. And remember, that one's got 4 lone pair bond pair and no lone pair interactions. Okay, let's go to the next one, which I bet was your favorite. Let's have a look at that one right there now. Well, count the lone pair 90-degree interactions. You'll say, nah, they're not any. Those things are 180 degrees apart. They aren't going to give us any trouble at all. Okay. Now let's count the lone pair bond pair 90-degree interactions. There's one. There's number 2. There's number 3. And now wait a minute. Do you see 3 more when you use the bottom unshared pair? You should. So how many do you see in all? You see a total of no lone pairs and 6 lone pair bond pairs. Now, look at the situation and tell me, folks, which is the best structure. And the best structure is going to be this one right here. Surprised? Yeah. That's going to be our best structure. All right, let's look at its actual shape now. Look at it like this. Now, remember, we take away lone pairs when we're considering actual shape. So, they're gone. Now, let's rotate this thing around so we can see it a little better. There it is. It's called a T-shape. A T-shape. Now, here's a thought question for you. What stabilizes that shape? What makes it hold that position instead of shifting those chlorines as far apart as possible? Along that same line, let's find the shape for ICl4. Now, what's the geometry around iodine and ICl4 with a plus charge? Figure it out. Did you get 7 plus 4 minus 1? Don't forget, you've got to deduct 1 for that positive charge. Minus 1 is 10 divided by 2 is 5. Yeah, it's trigonobipyramidal. Okay, there are two possible structures. We can have this one. Now let's look at this. Do you see 3 lone pair bond pair 90-degree interactions? And here's the other one. And how many lone pair bond pair interactions do you see for that one? Do you see 2? Let me show you where they are. Here's 1, 2, and 3. And here's 1, and here's the second one for this. Now, of these, then, which is the better? This one right here. The fewer number of lone pair bond pair interactions at 90 degrees. This, then, is our preferred structure. Let's get rid of those lone pair electrons. Just get rid of those and look at this thing. How would you describe its shape? Let's rotate it and look at it again right here. Yeah, it's a seesaw. Do you see it? Yep, a seesaw. Here's a thought question. What holds it in that shape? What supports it there so that it is able to do that? Let's look at the geometry of SCl6, sulfur hexachloride. Now, I'm going to stop for a minute and let you figure it out. And did you get 6 from sulfur plus 1 from each of the 6 chlorines, giving us a total of 12, divided by 2 is 6. And when you look that up on the table, what does it show? It shows that the geometry is octahedral. All right, now what's this going to look like? Well, in our model, it's going to look something like this. You see then that the sulfur in the center is connected to each of the 6 chlorines, and the chlorines are each at the points of the octahedron. Maybe it will help you if you see it like this. Remember, all the angles are 90 or 180 degrees. And if you look at it like this, perhaps it will show you that octahedral structure better. See the 8 faces on this structure. That's right. And notice that there are chlorines at each of those points with sulfur in the middle. Well, perhaps a better way to show you would be with one of these models right here. Let's come over here and look at xenon tetrachloride. Don't think that it's because xenon is a noble gas that it can't react. Yes, it can. It may not produce a lot of compounds, but it will produce some. So let's look at xenon tetrachloride. Run the geometry now and see what you get. Do you get 8 plus 4 is 12, divided by 2 is 6. So this has a geometry that is octahedral. But I wonder what the structure is. Is it this structure right here? Or could it be this structure over here? Well, let's go through and do our usual work and see if we can figure out which one is best, or which one is the better structure. The one on the left has how many lone pair interactions? And the answer is, it doesn't have any. What about the one on the right? Does the one on the right have any 90-degree lone pair interactions? Yep, got one right there, sitting at 90 degrees. You don't even have to go any further. By that token, you know that this is your better structure. So look at that molecule. It's flat. Its actual shape, why, it's a square plane, just like this. A flat molecule, a square plane. Yeah. Well, let's change pace for a little while. Let's talk about the role of carbon. There's a whole area of chemistry called organic chemistry, which is the study of the carbon compounds. And you will get into the study of the carbon compounds in this course in the second half of the course. Now, carbon tends to form covalent bonds, but it doesn't form covalent bonds with just a few atoms. These compounds may contain sometimes hundreds of carbon atoms, without even talking about the other atoms that might be involved. But let's look briefly at some of the bonds of carbon, because there's a different way of dealing with it when we're talking about its molecular structure or its geometry. The characteristics of carbon are important to us. It has 4 valence electrons. It tends to form covalent bonds, and its most common electronic geometry is tetrahedral. But there are circumstances under which it will be trigonal-planar and linear. It doesn't always follow our VSEPR rules. But for our purposes, determining the geometry for carbon compounds is pretty simple. Let me show you how to do it. Consider this structure right here. Now I want you to look at the number of atoms each carbon bonds to. For example, look at this carbon right here. It is bonded to 4 different atoms. Not different elements now, just 4 different atoms. And the geometry is tetrahedral. Yeah. Look at this carbon right here. How many different atoms is it bonded to? It's bonded to 2 hydrogens and a carbon. It's bonded to 3 different atoms. Not different elements, different atoms. And its geometry? Trigonal-planar. Folks, it's just that simple. Here's a case. Look at all of these carbons here. All of these carbons, each one of them is bonded to 4 different atoms. All of these are tetrahedral. And if you can imagine replacing some of those white hydrogens with the black carbon atoms, you can see this molecule extending on and on. C4H10. The geometry about each carbon is what? That's right, it's tetrahedral. Look at the number of atoms each carbon bonds to here. Look at this one. How many different atoms is it bonded to? It's bonded to 2 atoms. And what is its geometry? It is linear. It is linear. Now sometimes these molecules will get really big, and it can be trigonal-planar in one place and linear in another and tetrahedral in another, depending on which carbon you're talking about. So we take these carbon by carbon. Look at glucose, and look at the number of atoms each carbon bonds to. Now, we don't always show this in a nice geometric way. We lay it out pretty flat so it's easier to write or easier to type sometime. Look at the number of atoms that carbon bonds to. How many is it bonded to? It's bonded to 4 atoms. It's bonded to 2 different carbons, an oxygen and a hydrogen. Yeah. The geometry around that is tetrahedral. Look at this atom right here, this carbon. It's bonded to what? It's bonded to a hydrogen, another carbon, and an oxygen. It's bonded to 3 atoms. It doesn't matter that one of them is double bonded now to you. It's bonded to 3 atoms. Its geometry is trigonal-planar. Do you have the idea? That concludes this lecture. In the next lecture, Lecture 2, we're going to talk about valence bond theory, a better way to teach and learn chemistry.